Is it looking okay now? Wait, now it's not a stream. What does that mean? I ended it. Does it work now? Oh no. Oh, why is streaming so hard? Why is it so difficult to stream? It works! Oh, that would be good. Okay, wonderful. $1440p. You're last spoiled. Okay, wonderful. I guess I'll wait a few minutes just so that everyone who was in the other stream can get to this stream. I got myself some fried chicken for dinner today. Really wanted some of that Korean fried chicken. The problem was I didn't have any rice, so if I wanted to order some fried chicken, I'd have to go buy some rice and then cook it. And then maybe I'd be late for this stream. So I thought I would just get some rice from the place itself. But they don't sell plain rice unless you get it with some other dish. But none of the dishes you can get with rice were fried chicken, so I was real sad. So I had to get like one of their special fried rices instead. I had to get the kimchi fried rice, which admittedly was really good, but they managed to upsell me like to a $40 order, which feels bad. Turns out I am not immune to clever marketing. The kimchi fried rice was really good, I must admit. I've never had kimchi fried rice before, and I don't know what I expected, but it was literally fried rice and they put kimchi in it, like a lot of kimchi. Now I'm like sweating quite a lot because it was a little bit spicy. Although it might just be because I turned the aircon off like half an hour ago. Okay, I think that's enough stalling, so let's get straight into it. Alright, square root decomposition. This is one of those really weird topics in informatics because it's kind of really overloaded. There's lots of related techniques and ideas that people just together call square root decomposition, even though there's like 4 or 5 different separate things in there. So I'm just going to go through all of them. Alright, so the first and most basic technique, in my opinion, is bucketing. So depending on who taught you range trees and stuff, you may have already come across this idea. But okay, so the setup is some big text. You have an array and you have to facilitate operations of the form give sum of range of the array. So you all know how to do this one already. It's a cumulative sum thing. You can also slap a segment tree on it, which is a bit overkill, but let me show you a different way to do it because that's a fun thing to do. So let's say your array is something like, let's get some good random numbers in here. And 300. Oh, that's not really long enough. Let's make it a bit longer. Okay. Those numbers are too hard to add. How do I make this go away? Okay. So the naive solution is for each of your queries. Let's say there's a query that goes from like 12 to 300. the naive thing you can do is to simply iterate from left to right and just total up the numbers in the array. But of course, this is really slow. It's order n in the worst case when your range is really big and is pretty much the whole array. So what you can kind of do is to say, well, what if I grouped up the numbers into a bunch of separate blocks, and for each block I pre-calculate the total sum of that block. So for example, the total sum of this block is like 21. So some of this block is something like, I don't know, 380-ish. And the total sum of this block is 183. Oh yeah, when I said that there's a special machine learning algorithm, I meant me, a human. I just looked through your leaderboard submission. If it's not square root, then I would do something. I don't know what I would do. Sure. Oh, what? I have to pay for premium? Okay, whatever. Okay, so you calculate the total sum of each block. You pre-calculate that, and you can do that in linear time. And now, whenever you have a query, let's say you want to find the sum of these elements. Again, when you go through and iterate things one at a time, you can say, all right, there's a 12, there's a 5, and then when you hit this block, instead of going through each of the individual elements of the block one at a time, you can just say, the total sum of this is 380, and you can skip that entire block and continue. So in general, for really large arrays, when you have lots of blocks like this, and you have large queries, then this can potentially save you a lot because you end up skipping lots of elements by going through all these blocks. So you save some iteration time there across these blocks. Now, the question is, how big should these blocks be? Because if you make them too big, so let's say you just had two really large blocks, then you don't really save any processing time, because if they had a query that's inside one of the blocks, let's say you had only 2 blocks and these were both of size n on 2, then you wouldn't be able to answer this query any faster than order n because it's all inside one block. And at the other end of the spectrum, if you had lots of really tiny blocks and so on, then when you get a really large query, you don't really save on any processing because there's so many blocks that you have to end up iterating over anyway. You could end up with order n in the worst case anyway if you have up to order n of these blocks. So you're kind of sad, and you're not really sure how big you should make these blocks. Well, it turns out we can be a bit more precise about this. Can I pan this? Oops. Yes. Okay, wonderful. So let's say I'm going to make blocks of size B. That means that if there are n elements in your array, you'll have n on B blocks in total. So now if we analyze the idea that we had before, where we had like an array and there were a bunch of blocks. 1, 2, 3, and so on. Then the worst case, in order to facilitate the range sum query we were talking about, it would take you might iterate over order B blocks each time. So each one of these blocks, oh god, each one of these is one block. And the thing is that if you look at both ends of your query, you might partially overlap a block. So you can see there's a partial overlap here. Oh gosh. A partial overlap here and a partial overlap here. And for these, because they only partially cover that block, you can't use your special pre-computed sum anymore. You have to iterate individually over the elements of the array there. But fortunately for you, that's limited by the total size. The total complexity of this is limited by the size of your blocks. So, oh, I got this the wrong way around. Yeah, So the number of blocks you iterate over is n on b in total, because we said that there are n on b blocks. And then you have to add on the ends of the query. Oops. So there's this end and this end, and each one you might iterate over b items in total. So this would be the total time complexity of your query. So the question is, how big should you make b? And it turns out if you set b equal to the square root of n, then this becomes n divided by the square root of n plus the square root of n. And n on the square root of n is just the square root of n. So in total, the time complexity of this approach is order square root n, which is pretty cool. It's not faster than the cumulative sum approach that we had before, or the segment tree approach, but it's an interesting idea. And this bucketing strategy can be more powerful than, can solve more complex queries than a segment tree or a range or a cumulative sum can. Does that idea make sense so far? Okay, I don't see any questions, so that looks good. Now, as usual, let's go back to our original problem and let's make it a bit more complicated. Yeah. So now we have updates again. Update. Change an element. Oh no, suddenly the problem is hard. Can I... Where is the... What's that? Can you move things? Yeah, so now that we've added updates, you can't do the cumulative sum approach anymore. You can still do the segment tree approach, and that would be log n per update and per query. But we'll see that we can maybe kind of do something a little bit kind of maybe better, but we'll get to that. Okay, so how do you update this structure? So let's just remember what we had in this structure. So all that we needed to do was to calculate for each of our blocks the total sum of the elements in that block. So if we were going to update something in the block, let's say we decide to turn this 300 into, say, 20, then all of the blocks other than this one stay the same. So the only thing you need to do is to update this block right here. And this number would change from 380 to something like 60 or 70, I don't know. But it only involves updating this. So, oops. So what is the total time complexity of that? Well, we have, each block is of size b, so it takes order b time to perform this update. And if we set b to the square root n, that means we can perform the update operation in order square root n. Does that make sense? So in total, we've established before that we can do queries in square root n, and updates also have an order square root n. And an update just involves updating the value of the block of the element that we changed. And queries work exactly the same. So that's how you can solve range sum queries with updates in order square root n per update and per query. This is still not better than range trees, but in some sense it might be simpler depending on the type of query to do square root decomposition instead. But there is one scenario where square root decomposition can kind of beat a range tree, and that's when the number of queries and updates are really imbalanced. So we've established we can do queries in order square root n and updates in order square root n, but there's actually a way we can do queries in order 1 and updates and are still in square root n. So here's how that works. I'm going to make a copy of this. What have I done? Order 1 updates is also possible. So I know that you can definitely do queries in order 1 and updates in square root n, and I would believe you can do it the other way around as well, but I haven't thought about it. But yeah, square root decomposition allows you to do some weird tricks like this. Okay, so let's go back to the structure we had before, where we had a bunch of numbers and we had a bunch of blocks. I know these don't really line up with, they don't all have the same number of things, but I just wanted more blocks to showcase the example. Although this is kind of messy now, isn't it? Okay, fine. Everything will have 4 things in it. So in the same way that we pre-calculated the sum of each of these blocks, a second thing we can do for each of these blocks is also to calculate the cumulative sum array of these blocks. So for this first block here, the cumulative sum array would be something like 1, 4, 16, 20, and the next block would be 8. So that's like 1 block there. Oh no. And the next one would be something like 8, 37, 337, and some kind of big number. Oh, these are all out of whack now. But yeah, so if you calculate the cumulative sum over all of these blocks, that means that when it comes to the query, dang it. Oh no. Oh no. What have I done? Okay, let me just quickly redo that. Apparently you can't redo in this app, or I haven't quite figured out how to do it. Something like that. Yep. So if you calculate the cumulative sums for each of these blocks, then that means when it comes to the query, so let's say we're querying over this range, we can skip through the blocks as normal, but when it comes to calculating the partial sums inside each block, we can do that in constant time simply by consulting our cumulative sum table that we have. And so same over here, to calculate the sum of these 3, we just consult the cumulative sum table that I haven't drawn here. So in that way, we've kind of taken this complexity here and this first bit is when we're iterating over the blocks. This bit is when we're iterating through each of the individual elements. We've turned that into order 1, which is really good, but it doesn't quite save us yet because we still have to do the iteration through the blocks. But one thing that we can do to fix this is just to do a second cumulative sum table, but this time over the pre-computed values themselves. So for example, in this case, I haven't left myself any room, which sucks. But in this case, the second cumulative sum table will be over these values. So it will be something like 20, 400, and 550. Oh, if I had more foresight, I could make these some really good numbers, but not quite. Okay, so when it comes now to iterating over the blocks, it's kind of hard to see with this example because there's only 3 blocks. So let me draw up a larger example. So it's 1, 2, 3, 4, 5 blocks. And let's say that these have value like, I don't know, 10, 5, 6, 30, and 100. Then cumulative sum table over these blocks would be something like 10, 15, 21, 51, 151. And so now when you have a query that's something like, let's say it goes from here to here, instead of having to iterate through these two blocks separately, you can just consult your cumulative sum table and realize I just need to find the sum of all of the blocks between this first block and this second block. Or maybe if your query was something like this, then you'd be asking for the sum of everything from the first block to the from the second block to the fifth block. And again, you can solve it in order 1 using the cumulative sum table. Something like that. So now, instead of having to iterate through all of the blocks and have this order n on b, we can cut that down to order 1. Order 1 plus 1. So in total, what we've done is we've turned the query operation into order 1. Isn't that amazing? I think so too. Oh, there's lots of H's in the chat. I've forgotten what that means. Oh, whoa, I remember now. Okay. So yeah, this is how you do updates, queries in order 1. So let's quickly go back and check that updates are still square root n. So when we do an update, what needs to change? So when we update an element in our array, let's say we're updating this one, then what ends up happening is we have to recalculate the total sum of this block. That's order square root n. We then have to recalculate the cumulative sum. Again, that's order square root n because the block size is square root n, and you can do cumulative sums in order n, in linear time, I mean. And we also have to recalculate the total, the meta cumulative sum that we had over all of the blocks. And because they are square root blocks, that's also square root time. So we can see that updates are still order square root n. So if you ever come across a problem for some reason that says that you have to facilitate, like, I'm not sure what the numbers would be, but something like 500,000 queries, but only 20,000 updates, then maybe you can apply square root decomposition here, and it would actually be faster than a segment tree. Although trying to differentiate those with time limits might be a bit difficult, but who knows? Yeah, the numbers have to get pretty big. I think if this kind of idea were to pop up in an exam, it might be more of in a interactive problem where your goal is to minimize queries or something, or updates, I don't know. But yeah, this is a neat idea to keep in mind. So one thing about implementing this that you should note is that you should never calculate the size of the buckets dynamically. You should just pick a number and stick with that, no matter how big the input is. So for example, if you're told that n was up to 10 to the 5, then square root of n is about 330 in the worst case. But I'll just set the bucket size to be 300 or some constant close to square root n, because compilers apparently do very well with optimizing things to do with fixed numbers. You could transfer. There's an IY 2019 square root decomp task. Interesting. Yeah. So that's the basic idea about this. Are there any questions about this solution? Okay. There seems to be some more unrelated chat. So it sounds like people are perfectly happy with this. In which case, I will move on to the second square root decomp technique. Okay, so far we've had a problem that's involved an array. How about a problem that involves a different structure, a graph? Oh gosh, drawing graphs in this is going to be real annoying. Okay. So the problem is, given a graph, I want you to count the number of 3 cycles in this graph. So for example, in this particular example, we have one 3 cycle here. We have a second 3 cycle here, a third 3 cycle here, and maybe I should add more edges. Right, maybe you have, oh, that's a bad color. Maybe you have something like this. So that means you have a 4th triangle, 4th 3 cycle here, and a 5th 3 cycle there. So in total, this example graph, which is really messy, has 5 3 cycles. And so your goal is to count the number of 3 cycles in the graph. Does the problem make sense? Okay, wonderful. So the naive solution is to go through every triplet of points and check if there is an edge between those 3 triplets, because every 3 cycle can be categorized by the 3 vertices at its corners. So in total, that's order n cubed. That's the one. Order n cubed. That's really slow. So we're trying to find a faster solution than this. So one thing you can do is, let's say that each vertex doesn't have very many neighbors. So for example, we'll say that every vertex has at most 10 neighbors. Can we do something faster given this restriction? And the answer is yes, we can. So what you can do is to say, oh gosh, I make this mistake every time. Yep. So if you consider a vertex and consider its neighbors, it has like a small number of neighbors. We can keep track of those in a hash table. So maybe its neighbors are like 3, 7, 8, and 9 or whatever. And let's say that this vertex is vertex like 5 or something. And we have another vertex. We consider its neighbor 9. So that means there's an edge between them. And 9 has some other neighbors. Well, if there is a triangle that involves this edge, then that must mean that 5 and 9 must be adjacent to that neighbor. So for example, this might be a 3 or whatever. So if we consider the neighbors that 9 has, maybe it's neighbors to like 10, 3, 2, and 8. We can kind of intersect these two sets and see which ones they have in common. So for example, they have 3 in common and they have 8 in common. So that tells you that in this structure, we have a 3 somewhere and they form a triangle like this. And there's also an 8 somewhere that's both neighbors to 9 and to 5. So they also form a triangle. So this gives us a new solution. For each edge, there's order E of them. We do this process of checking all of the neighbors in one endpoint of that vertex and checking it against all of the neighbors of the other endpoint and seeing how many vertices are in both of them, because each one of those is a triangle. So checking, if you add all of these things together into a hash set, then this takes order D time in total per edge, where D is a number of neighbors. So maybe we can make this D. So this solution is nice and fast when the number of neighbors is small. But you can imagine if you had a vertex that had 50,000 neighbors, every time you had to check that vertex, then it's kind of rip. So now you're kind of sad, but you can be happy again because your intuition is kind of that I mean, if there are lots of vertices, there can't be lots of vertices that have a high number of neighbors, because each edge can only contribute to the number of neighbors for 2 vertices. So if you had e edges, that means that at most the sum of the number of neighbors across all the vertices in the graph has to be at most 2e. So for example, if let's say you wanted to make a graph where each vertex has d neighbors, then, and if e is the total number of edges, then v has to be less than, each vertex has at least, if each vertex has at least d neighbors, the number of vertices has to be less than or equal to 2e divided by d, because you kind of have to distribute them across all of the vertices. So if we put some numbers into this, it's kind of like if you want each vertex to have 10,000 neighbors and you only have 100,000 edges, then you can only have 200,000 divided by 10,000 vertices in total, which is like 200 or 20 or something like that. Does that make sense so far? Okay, cool. Yeah, so if all of your vertices are really big, then you don't have very many vertices, which means maybe you can take this order n cubed approach we had earlier of checking every triplet and seeing if they form a cycle or not, and maybe that would run in okay time. The answer is yes, kind of. But you might have a graph that's a mixture of large vertices and small vertices. So you can't really just do one of these ideas and have it run in time. So what you can do is you can combine them together. So what we're going to say is we're going to split the vertices into 2 types. And large. We're counting 3 cycles in a graph. This is kind of big now. Can zoom out a bit? Yes, okay. So you split the vertices into 2 types, small and large. We're going to say that the vertices are small. Small if the number of neighbors, which is called degree, is less than or equal to d, where d is a number that we have yet to determine, but you can probably guess what it is. Large if degree is greater than d. And we're going to go through all of the edges. Yep. So for every vertex, if it's a small vertex, which I'm going to call, if one of the vertices is small, I'm going to color it red, and the other vertex is either large, which I'm going to color green, or it's small, doesn't really matter, then we can take the order D approach that we had before. So we just look at the smaller vertex and we check all of its neighbors, so it's like, and we just do the process that we had before, this one, where we check each of the vertices neighbors with the neighbors of the other vertex of the edge. And it doesn't really matter how many things are in here. Like there could be like lots and lots of things in here. It will still only be order D because looking up into a hash table or an unordered map is constant time. So if one of the vertices is small, the other one is small or large, doesn't matter, then we can do the order D approach. So what do we do when both vertices are large? Am I a bad person? I'm so confused. It's this one. Okay. So if both the vertices are large, then we're kind of in a bit of trouble. So instead of doing this process that we described before, we're just not going to do it. And after we've gone through every edge and either done this process or done nothing, then we're going to move on to the second stage of our algorithm. And the second stage of our algorithm is just to go through every triplet of do nothing. And then the second stage of our algorithm is to go through every triplet of the large vertices and do this process we described before, where we go through, where we just check for every triplet whether there is 3 edges between them in this triangle pattern. So even though this is order n cubed, where n is the number of vertices, we know that there can't be very many large vertices. In fact, we've established that there has to be at most 2e divided by d. So total time complexity of this would be order e divided by d cubed. I'm just going to ignore the constant factor of 2 that we had before. This one. So this total time complexity is ed cubed. So in total, what is the time complexity of this step plus this step? Well, that's just order ed, we do this for every edge, plus e on d cubed. And so this still might be really slow, so we have to pick our value of d very carefully. What should it be? Well, you might have guessed already by the title of this lecture that we should set this to the square root of something. And I mean, we already have e's everywhere in here, so we should set to the square root of e so things cancel nicely. So in total, on this side, we get e square root e. And on this side, we get e divided by the square root of e cubed. And that's just equal to e. As you've seen before, e divided by the square root of e is just the square root of e. And the square root of e cubed is e square root e. So in total, we've shown that this runs in e root e. And that's it. Are there any questions about this problem or this idea? Okay, cool. Yeah, this is pretty cool. The first time anyone sees a square root decomposition idea, they're like, wow, that's the best idea I've ever seen. But yeah, the trick is recognizing what it means to be small and large. So for a graph problem, it's kind of obvious when you're dealing with edges like this. This is going to appear in ACIO. Oh, I'm sorry I spoiled your problem. But yeah, the main art is trying to see how to apply the square root decomposition. And here is one example. So the problem that has this same idea, this same small and large degree on a graph, there's a problem in the worksheet called colored walkway, and it has pretty much the same idea. But you're doing something more complicated than just counting the number of something. So you have to figure out how to apply the square root idea to a more complicated context. But yeah. Is there anything else I wanted to say about this problem? Oh yeah, so when you're doing this, you actually end up counting each triangle more than once. So you kind of have to be careful about making sure you don't double count things. So with this approach here, you end up counting things, each triangle 3 times. Kind of. Well, maybe if you have like something like this, you have to be a little bit careful because you end up counting one triangle for this edge, one triangle for this edge. But then you skip this. You skip counting the triangle 3rd time for this edge. So you have to be careful to to make sure you count things the right number of times. And the other thing is that this algorithm I've described, not only does it run in order e root e, each time it does an operation, it adds at most 1 to the total count of the number of 3 cycles. So the existence of this algorithm, and presuming it's correct, tells you that there can be at most e root e 3 cycles in any graph, which is a fun little tidbit. Oh yeah, that's a good point. So the way that you actually determine what to set d to in these situations is, well, I think the lazy way to do it is just to say, I've seen square root decomposition before, so I'm just going to pick square root as my number. And when you chuck things in, it usually turns out correct. But the correct way to do it is to say that I don't want either the left or the right term to dominate my time complexity, so I want them to be the same. So if you set ed equals to e divided by d cubed, you can figure out that d should be square root e, as mentioned here. Oh, it's a nice animation. Dang, that's cool. Oh, it's one of those animations that it can be either turned in clockwise or counterclockwise, depending on like how you look at it. That's amazing. Yeah. Okay, so it sounds like there's not much more to say about this problem, so I'll move on to the next problem. So I've shown you big and small decomposition in one context, but let me show it to you in another context to really drive it in. So let's go back to arrays again. Everyone loves arrays, right? Dude, I don't know. The numbers don't really matter, to be honest. So I'm just gonna make them small to make addition easier. Okay. So again, you have an array and you have to facilitate operations of the form query. Oh gosh. Query. What is the sum of a range? Familiar so far, but the update is a bit weird. With the update, you're given a value k and an increment value v, and you have to increment, oh, I spelled that wrong. Oh, increment every kth number by v. How do I zoom out again? Yeah, you want to do that. So for example, if k equals 3, then you'd be incrementing the third number, the 6th number, and that's it. And if k was like if k was 7, you would just be incrementing the 7th number. Like that. You get the point. And so the question is, can you facilitate both of these operations together in order fast? Okay, so you've seen big and small square root decomposition before. So I'll give you a few minutes to think about this problem and see if you can figure out what our big and small things are going to be while I go and turn on the aircon. Gosh, I'm so sad. I just realized my order came with a bunch of like free pickled radishes or something. I just didn't eat them. Okay. So even if you can't see the full solution so far, there's really only a handful of things you can try. So we're gonna split the updates into two types. An update is small if k is less than the square root of n. So let's say the array has n numbers, and large if is the problem online. Well, the solution I'm about to present is online. I'm not sure if there is a faster offline solution, but I'd believe it if there was. And a query is large if it's greater than square root n. Oh, I lied. It's actually the other way around. A query is small if k is greater than or equal to the square root of n. Otherwise, it's large if it's less than the square root of n. And the reason for that is because we're interested in how many numbers the query actually changes in the array. So for example, if is this small? Okay, yeah. For a number for a operation like k equals 9, that's really easy because it only changes one element in the array, which doesn't exist. So it will change only this element or something. But for a query like k equals 2, that's really annoying because it changes n on 2 elements in the array. It will change like this one and this one and this one and this one. That changes a lot of things. So facilitating that operation is really annoying. Okay, so for large queries, for small queries, we can kind of do things really naively. What we're going to do is we're going to have we're going to have a range tree over the array, and it's just going to store it's just going to be a basic sum range tree that facilitates point updates. And the way we're going to use it is for each small update, we're just going to iterate over each of the numbers it changes and then just point update that in the range tree. So if I were to represent a range tree visually, it would be something like this. Oh, I've done it the wrong way around. Something like this. Okay, I'm sure you get the idea. But to facilitate an update, I would just literally go through each of the elements and update them in this range tree. And so if I want to figure out the total effect of a large query, I just need to go through and check the sum of a range in this array. So for a large query, I can figure out the total delta it caused in a given range by consulting this range tree. Does that make sense? Oh, I've got it mixed up again. I keep calling them large queries, but they're small queries. I'm so sorry. Okay, let me get this straight in my head. So the small queries are the ones that update a very small number of elements in total array. So for every small query, we're going to iterate through that small number of elements it changes and just update them in the range like you would a normal range tree. And to query the total delta of all the small queries of a given range, we just need to query the range of that range tree. Okay, so that's how you handle small queries. For large queries, it's actually a lot easier than, I guess conceptually, than the large query, than the small query. Gosh, I keep mixing them up. How do I want to draw this? Okay, so let's take one of the small query values. So let's say we look at k equals 3. That's a nice small number. We're gonna keep track of the total the total delta of all of the queries for where k equals 3. And the reason that's useful is because we know that in our array of values, like 1. You get the point. We know that whatever these values are, we know that every third element gets changed. Oh gosh, sorry. Oh, I've done it again. Why? We know that for every third element that gets changed, every third element gets changed. So with a little bit of math, we can figure out for any given range query, we can know how many multiple of 3 elements are in it. And if you know how many multiple of 3 elements there are in it, then we just multiply that by the total delta we've had so far for that particular large query. So if the total delta was like 10, and you can see that this array range has 2 multiples of 3 in it, we know that the total change in the answer caused by k equals 3 queries is 20. So if you want to figure out the effect of all of the large queries, you just need to iterate from k equals 1, 2, 3, and so on up to the largest large query, and just apply the change of that. Apply the total change caused, the total delta to the answer. And because we said that a query is only large if k is less than square root n, that tells you that we only iterate over square root n numbers. Okay, so in total, what's the time complexity of all of this stuff? So for this small part we were talking about, that's just order square root n. It's just a bunch of math and iterating through all of these values. And for this one, it's just we have to do a bunch of updates. So it's the total number of updates we do times log for the range tree. And for any given small query, because k is larger than or equal to the square root of n, that means that every time we update something, we're jumping square root of n. Each time we update something, the next update is at least square root of n away. That means there can be at most square root of n updates in total for any given query. So this is actually just square root of n. Oops, I've done this badly. Yep, so the total time complexity for... Oh, I've mixed things up, haven't I? Yeah, so I've kind of combined queries and updates in one. So let's do them separately. So for... okay, for updates, if we have to do the small query, then it's square root of n log n. But for the large queries, it's order 1. So small queries are square root n log n, range tree, and the small queries, and the large queries, sorry, are order 1, because all it involves is changing the total delta. So that's for updates. And for queries, it just involves one range query in the range tree, which is log, plus you have to iterate through each and every one of these deltas, which is square root n. So in total, you can see that the cost of the updates is the one that dominates because it has this square root n log n term. So in total, it's order q root n log n, where q is the total number of operations. I would have thought the math division constant would be pretty fast, but what do I know about the way the compilers do things? If you wanted to be super hacky about it, you could hard code like a statement for every number from 1 up to 300 or whatever, and hopefully the compiler optimizes the ones it can optimize away. it's worth mentioning at this point, in terms of implementation. Oh, that's nice. Oh, he was writing something, but then he deleted it and started writing again. Rather than trying to math it out, yeah, that's a good point. So if you pick a number that's near the square root of n, like the number I usually always pick is 300 because that's close enough. If that isn't fast enough and you're pretty sure the problem is a square root decomposition problem, then just start trying other numbers. I think I've seen one problem where even though the square root is 300, like the fastest solution had a block size of 50 or something like that. And it's because, as mentioned here, different parts of the algorithm take a different amount of time, and that can actually that can actually skew the bucket size or the square root size that you're looking for. But yeah, that's kind of where informatics becomes like this combination of theoretical computer science and like the way that things actually work in the real world. Okay, so are there any other questions about this particular idea? Dang, look at all these nice notes. Oh, I've drawn on this one now. Okay, wonderful. So let's move on to the third technique I wanted to talk about today. And that's batching updates or queries or whatever. Okay, so let's go back to the original problem we had. Range some query. So, oh, I feel like if you make the threshold between small and large, square root n log n or something, you might get a slightly better time complexity, but I don't know what I'm talking about. I think that you're right. I think you might want square root n, some function of square root n and log n, but I don't actually remember. I haven't actually done the math. But yeah, as far as the informatics is concerned, pick 300 and then adjust it up or down until you don't TLE anymore. Oh yeah, it might be something like the square root of n log n. Math is too hard for me. Okay, so the next problem, actually we're going back to a problem, the first problem that we had. It's range sum query again, and the update is the update's the same as well. It's point update again. So we're gonna solve this first problem that we did in square root time in order square root time, but a different way. I don't think it's any faster than the one that we had before, but it's a good way of demonstrating this idea of batching updates / queries together. And in this particular context, it's very important that the problem is offline. Okay, so let's start with another array. I don't know. Something like that. And this time, what we're going to do, because the problem is offline, we're going to look at the list of queries and updates that we get. So maybe we get something like, okay, if everything is indexed from 0, so that's index 1, 2, 4, 5, 6, whatever. Maybe the first thing we get is like query from like 2 to 4, an update from like 5. I want the value to become like, I don't know, 3 or something. And we get some queries again. So query from, let's say, 4 to 6, or whatever. And then maybe you get more queries or something. So what we can do is, remember before when the way that we answered queries quickly is by, you can answer queries quickly by using a cumulative sum. That's great, but you can't do updates to it, right? But you kind of can hack updates on top of it by figuring out what the answer is at the start and just replaying updates on top of your query to see how it would actually affect your answer. So, for example, the cumulative sum of this array would be something like 1, 5, 6, 11. Something like that. And so to answer the first query, you would just, from 2 to 4, let's say it's inclusive. So in this range, it would be something like 11 minus 1, which is 10. Oh no, what have I done? Don't press Ctrl Z. That screws everything up. So you can use the cumulative sum to answer the queries in order 1 without updates. But let's say you want to answer, so that lets you answer, did it again? That lets you answer this query in order 1. But this query, you're going to have problems because there was an update that happened before it. Well, if you kind of pretend that update didn't happen, you can just look at your cumulative sum again and you can go, so it was from 4 to 6. So the total sum would be like 28 minus 11, which is 17. The answer would be 17 if it weren't for the fact this update happened. So you can say, all right, the answer is 17, but there was an update. And the update changed this element from a 2 to a 3. And you can see that because the query window is from 4 to 6 and 5 got updated, this update would have affected our answer. What would have been the total effect? Well, because it changed us from a 2 to a 3, that means that our cumulative sum, the answer we got from a cumulative sum, is 1 less than it should have been for this answer. So you can kind of go through all the updates that happened before this query and just add or subtract the total change it would have caused. Does that idea make sense? So if there were more queries before this, we would have to go through each and every query and check how it affects our answer so far. Okay. So in total, the cumulative sum is order 1 plus u with updates, where u is the number of queries that happened before us. So number of queries. So obviously, this works okay for like the first few updates, but once the updates start to stack up to a really high number, then you're kind of screwed again because this ends up basically being linear time. That kind of makes us sad. But what you can do is after there have been a lot of updates, we can say, all right, it's time to stop and rebuild the cumulative sum so it's correct again. So if you have a sequence, so you can kind of look at it like you have a sequence of queries and some updates. Okay, sure, something like this or whatever. And well, this query, all these queries are kind of free in a sense because they don't have any updates to apply. But this one has 1 update to apply. That looks like a 2. 1 update to apply. This one has 2, 3, 4, 5, 6, 7, 8, 9. So once you get to kind of like this query and beyond, we're starting to have to apply lots of stacking updates at a time. So if we decide at this point, we're going to rebuild our cumulative sum. At this point, we're going to rebuild our cumulative sum. That means that this query is now going to cost us, this update is going to cost us 1. Let's not draw over that. Now that we've rebuilt the cumulative sum, this update will cost us 1. This will cost us 2, this one 3, 4, and so on. So after we rebuild it, the cost of all the updates that happen after us kind of get reset. So it doesn't kind of build up to being linear time as we did before. And as you might have guessed, we should rebuild it after approximately every square u queries. Square u updates, I mean, sorry. So if you can kind of imagine that this here represents the block of all of the updates in the entire problem, then every square u updates, so that's like square u, we're going to rebuild our cumulative sum. And the reason this is useful is now each and every one of our updates will cost us at most order square root u. Because each of these blocks has a most square root u, we only have to replay square root u queries on top of what we have so far. So each query can be answered in order square root u. Does that make sense so far? It sounds like the answer might be yes. Is there anything that doesn't make complete sense? So that makes queries nice and fast. But the question is, can we really afford to update? Can we really afford to rebuild our cumulative sum so often? Well, if we're going to update it every square u queries, then that means that the number of times we have to rebuild our cumulative sum is u divided by square root u times, because that's the number of blocks that we have, minus 1. And each time we rebuild it, it's going to cost us order n in total, because you can build the cumulative sum array in linear time. So if you have like a separate array that keeps track of what the actual array is at any given point as you go through the updates, then you can rebuild the cumulative sum in order n just by literally going through what the array is supposed to be. Just to clarify, the square root size for all test cases is fixed by the max u. Yep. So in practice, instead of rebuilding it every square root u queries, or every square root u updates, you'll just rebuild it after every 300 updates, or whatever constant you determine to be efficient. Yep. So u divided by square root u, that's actually just square root u. So in total, you've managed to solve, this is total updates. No, this isn't quite right. Updates are order 1, because you just record the update, and then these rebuilds you do, which are kind of separate from the queries and updates, that's order n square root u in total. So we've managed to solve this in better than the naive solution. Okay, does that idea make sense? Now that I think about it, there's no reason this needs to be offline. You can do this online as well, because all you're doing is just going through the queries and updates as they happen. I don't know why I thought that this needed to be offline. That is just a lie. You can do it online as well. I was just seeing if any of you were paying attention, and you all have failed because you didn't mention it. Okay. So that was a basic example. It's kind of contrived because you can always just implement this using a segment tree, so it's not really that useful, but hopefully it's instructive of the general idea. If online you don't know the u. I guess that's true, but usually you just take the maximum u in the problem statement. So if the problem statement says u is like between 1 and 100,000, you just rebuild every 300 queries or whatever. Okay, So hopefully the idea makes sense, in which case I'll move on to a slightly different example. Okay, so imagine you have a deck of cards. This one. Deck of cards, they go from like, dude, I don't know, 1, 3, something like that. That's a very short deck of cards. You have to facilitate a bunch of shuffling operations. Each shuffling operation takes a range of cards and deletes them and moves them to the end of the array. So for example, that's one shuffling operation, and maybe the second shuffling operation is something like that. And maybe the third shuffling operation is something like that. You get the point. You basically take a subinterval of the array and you just move it to the end and everything shuffles up. And so the question is, after a bunch of these shuffle operations, what is the final state of the array? Okay, I'll give you all a few minutes to think about it, having just learnt about batching updates, and I'll go grab some water or something. Yes, there are no queries. You just have to update just have to output the final state of the array. Yes, that's true. You can solve this with a treep or any SBBST, but you don't want to implement one of those because it's nasty. Or you have like 6 seconds left in the exam or something. I don't know. If you can implement an SBBST that lets you perform the operation of splitting out a sub-interval of your SBBST, or basically splitting it at some split point, then it's pretty trivial to perform the operations literally as described. My tree implementation is almost as easy as the seg tree. Damn. Then you'll absolutely be prepared for the 6 tree problems we have in the selection exam. Okay, you've all had some time to think about it. So I'll just go ahead and tell you how to do it. Okay. So what we're going to do is we're going to keep track of kind of the ranges of things. So if you can kind of imagine this, instead of the arrays being arbitrary numbers, let's just say for the sake of thinking about this problem, that they're all just numbers from 1 up to n. The problem doesn't really change if they're not. So the way you can kind of think about this is, you can think of the compressed form of this array as just being, it contains numbers from 1 to 10 consecutively. And so when you have a split operation, let's say they want you to split out the second and fourth cards and put them at the end, then you can kind of imagine this as being like, you take this, you split it out into like the first interval, the second interval, which you're cutting out, and then the third remaining interval, which goes from 5 to 10. And you're being asked to cut this out and move it to the end. So if you compress the consecutive ranges of the array, now they look like this. It goes from 1 to 1, 5 to 10, and 2 to 4. And the way that you can do this is, you can do it kind of naively just by iterating through each of your each of these ranges and figuring out where the cut points lie just by keeping track of a total count of the number of elements so far. So for example, if you're asked to cut again and you're being asked to cut from, say, the fourth element to the fifth element, then you would notice that, well, this range contains one thing, this range contains 6 things, so the cut at the fourth point will be 3 elements into here. So it would end up looking something like, so the fourth element here, 5, 6, 7. So the first cut point would be, that'll be from 5 to 6. And 7 is the next element where things start again. And how many elements did I say we're cutting out? I don't know, let's say we're cutting out 2 elements. So this would be 7 and 8. And the remaining bits would be 9 and 10. So we kind of split this 5 and 10 into these 3. And then you have to move this, to the end. And so it ended up looking something like that. Now things can kind of get complicated when you're trying to cut out an interval that spans several things. So if you had to cut something like this out, then this would end up being like 5 to 5, 6 to 6, and then let's say you're cutting out 7 to 7, and then you just have 8 to 8 at the end. Now when you're moving things, you have to move, and now when you're moving things, you have to kind of move, like, you end up having to move like this whole range of things to the end. So it would be something like this. So implementation wise, this isn't completely straightforward, but you can afford to do it in linear time just by iterating through everything, as you'll see in a moment. Okay, so does this like concept of ranges make sense so far? Are people comfortable with what these ranges mean and how they represent the original array? Okay, cool. So the thing about this is that the cost of doing any one of the shuffling operations we're required to facilitate, it's order k, where k is the number of ranges that we have so far. So while the number of ranges is small, this order r is small enough that we don't care. But once the number of ranges becomes a lot bigger, then the order r factor is a lot larger. So what we can do is we can kind of recompress things after every square root s shuffling operations, if s is a total number of shuffling operations. How does that actually work? Well, the original array we were representing is the numbers from 1 to 10. So the question is, after all these shuffling operations, what does the array look like now? That's actually pretty easy to do. You just need to iterate through all of these ranges and figure out and kind of write out what each of these ranges represent. So the range from 1 to 1 represents the number 1, the range from 5 to 5 represents number 5, and so on. This range represents the numbers from 9 to 10, and then you have 2, 3, 4, and then you have 7. So this is what the final array actually looks like after you've applied all these operations and got these ranges. And so what we can say is, we can say, all right, let's pretend that this is the new original array, And so 1 to 10 kind of represents this array that we had before. So you can kind of think of this as like an index into the array, into your new array. So this is like 1 prime and this is like 10 prime, where prime is like this array here. So now that we've kind of rewritten what the array we're referring to looks like, we get to do this nice thing of representing our range with just this one single range. And now when we do the cutting operations again, because we're referring to this new array, the cutting operations are fast again because we're only starting with one range. So again, the number of ranges we're dealing with after each cut is like 1, then next time it's at most 3, next time it's at most 5, and so on. And so we're getting the nice fast operations again. So if we do this every square root s shuffling operations, then in total, we only ever have to do, each shuffling operation only takes order square root s in total. Does that make sense? Oh no, someone is typing. That means they have a comment. Oh, but they've stopped typing and now they've started typing again. I don't really see how to do updating thing in time proportional number of ranges. Can you go over it again? Yep, sure. So let's say you have a bunch of ranges. 1 to 5, like 7 to 6. Oh, that doesn't make sense. 7 to 8, and let's say 20 to 30 or whatever. And let's say we have like, I don't know, 10 to 15. Yeah. I know not all the numbers are accounted for in here, but for the sake of this explanation, it doesn't really matter. So what you can, let me add some metadata to this to make things a bit clearer. Yellow. Oh, I keep doing that. Why does it do that? It's the interface that's wrong. Okay, so this range from 1 to 5, that contains 5 numbers. This range from 7 to 8 contains 2 numbers. It sounds like some other discussion is going on there, so I'm going to ignore that. This range has 11 things in it. This range has 6 things in it. Okay, so let's say you want to cut out all the elements from the range okay, let's say the next operation we want to facilitate is to cut out everything from the 6th element to the 15th element. Yeah. So the question is, where exactly are we cutting to make our new ranges? So we can move everything between the 6th and the 15th element to the end. So obviously, if the 6th element is part of the middle of some range, we're going to have to cut that range in order to be able to move just the 6th to the 15th elements to the end. So where does the 6th element fall? Well, this range has 5 things in it. This range has 2. So it's going to be inside this one because it's not inside the first one because it's only got 5 elements. And we know that it's somewhere in the first 7 elements because it's the 6th element. So we can kind of walk through our ranges and figure out where that is. And once we do, we can just take the range that it falls into and kind of split it where that 6th element would be. So in this case, the 6th element is 7. So we'd have to split it at 7. So we get a range from 7 to 7 and a range from 8 to 8. And similarly, to find the 15th element, it would be inside this range. Do you need linked list? You do not need linked list. You don't need these operations to be fast, right? Because you can afford to just iterate through everything and insert and remove things really slowly because we're only aiming for order linear time at the moment, right? Because the whole time complexity of this entire algorithm is kind of based on the fact that I hate that it selects everything. You can't unselect it by clicking on it like you're supposed to. What was I saying? Yeah, so what we're doing is we're trying to perform the shuffle operation where we take some subarray and move it to the end. We only need to perform that in linear time to the total number of blocks that we have. Because we're doing this rebuilding thing every square root blocks, the time complexity doesn't end up being bad because of the linear time shuffling that we do. So yeah, I guess what you're saying when you're asking do we need a linked list is because when we're doing the split operation, we're kind of inserting into the middle of our list of ranges. You're right, that's slow, but that's okay because we can afford to insert into the middle of our vector or array or whatever and have that take linear time because we end up walking through our array in linear time anyway. So it's fine for it to take linear time. Does that kind of clarify your concern? Wonderful. Yeah, so I guess I'll complete this process for completeness. So now we have to split out the 15th element as well. 5, 7, 18. So that means that it's going to be inside this range. There were 7 elements before it. So that means we'll be splitting at the 8th element in this range. So that would be element 27, I think. I think I might be off by 1, but that's the concept should be relatively the same. So this here is our 15th element. This here is our 6th element. And this consecutive block of 3 ranges represents the range from 6 to 15. And then all we have to do is just take these 3 ranges and put them at the back. And again, we can afford that to do that in linear time because that's the time complexity we're aiming for. So that's in more detail how you perform the actual shuffle operation in order linear time. Yep. Are there any further questions on that? Hopefully that explanation made sense. Let me know if it doesn't. But yeah, so if you have that operation, then if you kind of do this re-indexing thing every square root number of shuffles, then in total the time is going to be s root s root n. I think it's n plus s root. Yeah, I think it's n plus s root s plus n. I don't know. Let's figure it out. Okay. So in total, each of these operations, in the worst case, we have square root s things, and we do it once for each shuffle operation. So it's s square root s to do the actual, to apply the actual shuffling operations. And to do the reindexing, it takes linear time times square root s, because that's the number of times we do the reindexing. So yeah, in total, this takes us order n plus s root s, where, oh dang it, where this part is applying these updates, and this part is the reindexing. Yep, and that's how you can implement this in using square root decomposition. Okay, cool. Hopefully that makes sense. In which case, hopefully that showcases how you can use the concept of batching updates together and periodically doing some kind of recomputation to speed up your the problem. Okay, so the last technique I wanted to talk about in the realm of square root decomp is Mohs algorithm. Some of you may have already heard about this one. So yeah, Mohs algorithm, this one I know for sure you can only do for offline problems, and it's actually quite limited in scope. So what you're looking for when you want to solve a Mohs problem is, it's a problem that has to, it applies to any problem that is offline and there are no updates. So it's kind of pretty obvious, in my opinion, when a problem is a Mohs algorithm problem. If it fits these two criteria, then the Mohs idea might apply. Yeah, but just because a problem is offline and has no updates doesn't mean that you have to do it with Mohs. There might be a faster solution, and indeed the time limit may be such that Mohs isn't allowed to pass. It's always hard to tell with square root decomp problems whether a particular solution is going to succeed or not, I find sometimes. Yeah, in some problems, when you can do, even if you can do it with a segment tree, sometimes it's just simpler to do it with Mohs. Wacky queries equals Mohs. Yeah, if you see a query that you definitely can't figure out how to do with a range tree easily, then Mohs might be able to help. Okay, but let me just go through an example. Oh, what? I don't have an example of a problem in my notes. What was I thinking when I wrote this? Okay, I'll just do the standard problem. You want to do OMO? I don't want to spoil OMO. Okay, so query given a range, so you have an array. The query is given a range. Determine the most frequently occurring element. It's like the classic problem. Okay, so for example, if you had a range that was like, if your query is over something like this, for example, the answer would be 3, because 3 occurs the most number of times out of all the elements. 3 occurs 3 times, 2 occurs twice, but 4 only occurs once. So the answer is 3. Okay? So, and you're given a bunch of queries that you have to answer, and they're offline. So if you haven't seen Mohs before, so maybe, I don't know, maybe some of your queries are like this or whatever. And there's like this query, and there's lots of them. Okay, so when you look at this problem, you're kind of not really sure how to approach it, But one thing that might occur to you when you're looking at this is maybe you can kind of do a sliding window thing. So let's look at a sub problem of this original problem. So it's the same query, but all ranges have length k, which is fixed. So that means that in the original problem that we had, can I erase lines? Oh, it erases words too. So let's say k equals 2 or whatever. That means that every range only ever covers, let's make it 3. Maybe k is 3. That means every range only ever covers 3 elements. So for example, this might be a range, this might be a range, this might be a range, and this might be a range. And so what you can do is if you sort your queries by their starting point, so in this example, your queries would be something, if you sorted all these queries, then you'd look like something like this. That's really messy, so let me erase some of these lines. Yeah, so if you sorted all the queries, you'd get something like this. I should have made this a bit bigger. Oh, this is much nicer. I should have been using this the whole time. Yeah, all your queries look like this. Then you can kind of see how nicely they relate to each other. Each query is like, you remove like one element each time, and you add one element each time. That's how you can go from the previous query to the next one. So let's say you had a structure that kept like a count of all of the elements in this range. So your structure would be something like, for the first range, it would be something like 2 occurs once, 3 occurs once, and 4 also occurs once. And so if you wanted to remove this element, this 2, you would just go ahead and set this count to 0, which you can do with your standard unordered map. And you would go ahead and increment this count, increment the count of 3 to add on this new element. So 3 becomes 2. So that's how you can kind of keep track of like the set of elements as you kind of slide this range along. And the second difficult part is you have to be able to keep track of the most frequently occurring. And so what you can do is, as you're kind of like changing these numbers, you can have a set of all of the counts you have so far. So you have a count 0, count for 0, a count for 3, a count that's 0, a count that's 2, and a count that's 1. And because sets can give you the min and the max in logarithmic time, you can keep track of the max really quickly. And whenever you change this, so like maybe this becomes like a 3, you just delete the corresponding element in the set, and then you add the new value of that. And so that's how you can keep track of the max of this unordered set, of this unordered map, I mean. So that's how you can solve this problem offline if all the queries have the same length. But the problem is that all the queries don't have the same length, right? But maybe you can apply a similar idea. So in this particular example, each time we go from one set to another, we delete the leftmost element and we add the rightmost element. Delete the leftmost, add the rightmost. And this example didn't show it very well, but we didn't say every query had to be in our set. So maybe this query wasn't here. So to get from this second query here, this second query here to this third query here, we actually end up having to delete 2 elements and add 2 elements. But the point is to get from one query to another, it's you delete from the left and you add to the right. But the operation I described here it doesn't necessarily require that you delete from the left, and that you only delete from the left and only add on the right. You can actually delete or add from both sides, and the algorithm is basically the same, right? So if this is the range you have so far, then you could extend the range by 1 on either side by applying the same idea we described, or you could delete one element from either side, applying the same idea we just described. If queries are offline, does the order still matter? Because they're offline, that's the reason we are able to sort them and make the order not matter. Because we can process them in whatever order we want, it just kind of makes sense that we want to process them in some kind of sorted order. It's kind of like how if you're given a problem where the order doesn't matter, a natural first step is to sort things and see what falls out from there. Worth noting that it's possible for the left index to move backwards. Yep, I think that's what I was describing here, unless you're talking about something else. I'm not sure what discussion is happening here, but I'm just going to continue, and if people... I thought you were talking about output order. I'm not sure what I've missed in this chat. Okay, I'll just continue with my explanation and you can clarify if there's something that doesn't make sense. Yeah, so the basic idea is if you have a range, you have to output queries in the order they appeared in before sorting. Yeah, so I guess when you sort the queries, you have to keep track of what order they actually originally appeared in so you can output the answer in the correct order. Because usually, even if the problem is offline, it's phrased in the context of you're given a series of queries and you have to answer them in order. Yeah, you have to store the original query order. The most natural way to do that is, in addition to the left and right end of each query, also store the order, the index that it comes with in the input. And then when you go to answer when you actually go to output the answers, you can store them into an array and put them at the position in the array that they would have been if you outputted them in the correct order, and then just output that array. Yeah, the ID of the query. So yeah, so when you have like this structure for some range, you can get the structure for any, in some sense, adjacent range to this current one, where adjacent means it differs by at most 1. Either you add 1 or you delete 1. Add 1 or you delete 1. So that should be that or that. And so in some sense, if you have the answer for one range, you can convert it to the answer for any other range, like this one for example, simply by shifting the left and the right endpoint in the appropriate direction. So for this example, you'd shift it this way. For an example like this, you'd have to shift it like this, and you get the idea. I'll just draw in the last one for completeness sake. You just shift the left and the right end in whatever direction is appropriate to make things work correctly. So that gives you a way of taking this sliding window idea we described earlier and applying it to arbitrary queries. Now, while this is a correct solution, it's not particularly fast if you don't order things correctly. And the reason is because what if you get a query that's something like this? So there's your first query. Here's your second query, third query, fourth query, and so on. So each one of these, whenever you move from one query to the next, you have to go like all the way out here, and then you have to come all the way back. And then you have to go all the way out again, and all the way back, and so on. So in doing this, it ends up taking you order n time per query, which is something that you wanted to avoid in the first place. So now you're really sad. But the trick is actually really simple. All you have to do is to find a sort order for these queries that makes this not slow anymore. Okay. So as you might have guessed, the title of the lecture is square root decomposition. So it's going to involve breaking things up into square root blocks in some way. So I don't really know how to motivate this, so I'm just going to tell you how to do it. So we're going to divide the array up into chunks of square root. So each of these is square root in size. And so on. And what we're going to do is we're going to group the queries into buckets based on which one of these square root buckets that the left point of the query starts in. So for example, the first batch might be all of the queries that have a start point in this first bucket. The next batch of queries are all the ones that have a start point in the second bucket, and so on. You get the point. And the third bucket, again, it looks something like this. Who knows? And the fourth bucket will be, I've used the same color twice, I think, but they're different buckets. Will be something like this, whatever. Yeah, so we've grouped them into these buckets. And so the reason this is kind of nice is, let's look again at what actually happens with the left and the right endpoints of each of these queries. So let's focus on one of the buckets. Let's say this one. What happens to the left endpoint? Well, it does end up having to move backwards and forwards, but because every query inside this bucket is inside a bucket of size square root, we know that each time we have to move it, we end up having to move it at most square root elements. Yeah? So each time the left pointer moves, it only moves a total distance of square root per query. So that's good. That means that we're on our way to making a problem with a total amortized complexity of square root. But the problem that you're faced with is the right pointer. The right pointer could be absolutely anywhere. So you could end up with the problem of having to shuffle backwards and forwards like a lot, like we said earlier. That makes you really sad. But what you can do is, after you've bucketed every query into its square root bucket, you can order the queries inside each bucket according to the right endpoint. So this might end up, if we order things in ascending order of right endpoint, then your queries might now look something like this. Oops, that's too far. So now, even though we do have to end up moving, we might end up moving really far in any one particular jump between two queries, we know that in total, we're not going to move more than n, because we're only ever moving to the right, because the right endpoint is always increasing, and we are going to hit the end of the array eventually. That's really nice. So that means in total, if we sum up the total green movements per query, that's, can I change the color of this? It's order square root per query. And for the, I don't think you can change the color in between. So for the left endpoint, it's order square root per query. For the right endpoint, it's going to be order n per bucket. And because each bucket is size square root, that means there's going to be square root number of buckets. So there's going to be square root n. So inside each bucket, the left pointer moves q root n, and the right pointer moves almost n root n. So that's really nice. And I guess the last thing to talk about is what happens when you move from one bucket to the next. So we've accounted for all of the movements between two queries in the same bucket, but now what about the queries that move between buckets? So like this jump, and this jump. Well, we don't have to think too hard about them because there's square root buckets. It's wrong color. Because there's only square root buckets, we only have square root n of these queries to think about, and each one, sure, fine, it can take order n in the worst case, but that's still only n root n in total. So we're good there. So yeah, in total, if we order things in the way described here, then performing this procedure of going from query to query by extending or contracting the left and right ends takes at most order n plus q root n. And we're done. That's the entirety of Mohs algorithm. Mohs algorithm can be summed up in this one singular diagram here. So one small implementation detail is how do you actually group the buckets like this? So what you can do is you can figure out, so for each of these queries, you reduce it to a pair where the first element of the pair is the index of the bucket it's supposed to fall into. So for this first query, it would be 0. And the second element is going to be the right endpoint. So this right endpoint might be at position like 15 or something, whatever. And so if you do this for every one of your queries, then you can sort these first by their bucket number, and then if the bucket numbers are the same, you can sort them by their index number. And that will give you precisely this ordering that you're looking for. Yep, and that's Mohs algorithm. And so with Mohs algorithm, you can solve this really weird query of determining the most frequently occurring element in a range, which is not something that you'd be able to do with a standard range tree. Or with any range tree, I think. I don't think any range tree can facilitate this operation. So in general, Mohs algorithm can be used when, of course, it has to be offline. It has to have no updates, as you need to be able to sort the queries. But the way that you know that you can do a particular query using Mohs algorithm or not, it is based on whether you can extend or contract any endpoint of the query at will. If you can do this kind of extend or contract, and the problem is offline, it has no updates, you can apply Mohs. Yep. So are there any questions about Mohs algorithm? Range tree of hash tables. I don't think a range tree of hash tables is going to help you here, because as you go up in your range tree, let's say you have a node that covers like 16 elements, your range tree can have like 16, your hash table can have like 16 things in it. Oh, okay, you weren't being serious? Or you realized that it's not going to work? Yeah, the problem with a range tree is that you need to keep track of like the count of all the elements in this range, and it can be quite large. Yeah, okay. My apologies. Mohs algorithm of seg tree beats. I think that's also a joke, but yeah, I don't think segment tree beats is something that will help you here. Okay, wonderful. Are there any other questions about Mohs algorithm or anything else that's been discussed so far? Dang, look at all these notes. All these really useful notes. Oh no, I've zoomed out so far that I've lost it. Oh gosh, I can't find it anymore. How do I center? Oh, okay, wonderful. Seeing as Pat mentioned seg tree beats, what are they? So there are some like additional operations that initially might surprise you that you can do with segment trees. And the way they work is they rely on, even though any one particular operation is slow, might be slow, they amortize out using some pretty gnarly analysis. Well, it's not that bad, but it's probably more complexity analysis than you're used to. I think I remember there being a really nice segment tree beats. Oh no, you're gonna see what YouTube recommends to me all the time. Yeah, there's a really nice, oh, I shouldn't play this, it's gonna echo. There's a really nice tutorial on that if you want to learn about it. But yeah, it lets you implement some interesting segment tree operations you wouldn't otherwise be able to implement. Okay. Are there any other questions about scrote decomposition? If not, then I think that's all that I had to talk about. Thank you everyone for joining in on this lecture. Would you mind posting the link in the chat? Oh yeah, of course. Thanks everyone for joining in on this lecture, and hopefully you should be able to solve all of the problems in the set now. Happy training. I'm going to cease to exist in like 6 seconds. And by 6 I meant like right now.